In this video, we are going to do another Lagrange multipliers example. So the example says, let's find the maximum and minimum values of the function f of x comma y equals x squared plus y squared minus 2y, given that x squared plus y squared needs to be equal to 9. So I want you to try this question first. So we've done a few examples now together, but I want you to try this problem first. So pause the video for 4 minutes to try this question on your own. It's probably not going to be enough time to finish the question, but I mostly care about do you know how to start the problem and what the key ideas are. So 4, 3, 2, 1, pause the video. Pause the video and try this for about 4 minutes. Really take this opportunity to try this problem. See how well you understand these Lagrange problems. Alright, so hopefully you've done that. Hopefully you've paused the video for about 4 minutes to really try this question. That's really important. Okay, so the first thing that I want to point out is when a problem says, tell me the max and min values, this means that it wants to know the outputs of the function. So it doesn't want to know just what the x and the y values are that give me the max or that give me the min. It wants to know what I get out when I plug those x and y values into my function. So at the end, I need to get those outputs. Okay, so we know what our function f is that we're trying to maximize or minimize. Let's get the function g. So g comes from the constraint, and this is the constraint. And by moving everything over to one side so that the other side equals 0, and when we do that, we get g of x comma y is equal to x squared plus y squared minus 9. Now I want to take the gradient of both functions. So the gradient of f equals 2x it's the partial with respect to x first. And then the partial with respect to y is 2y minus 2. Then take the gradient of g. So the partial with respect to x is 2x. The partial with respect to y is 2y. Alright. So now we set the gradient of f equal to lambda times the gradient of g to get a system of equations. So from their x components, I'll get, from gradient of f, I'll get 2x. And then this is going to be equal to lambda times the x component of gradient of g, so 2x. The second equation will be, so the y component of gradient of f is 2y minus 2. And that's going to be equal to lambda times the y component of the gradient of g, which is 2y. Okay, so those are the equations that we get from setting those components equal. But there's one more equation. The other equation comes from the constraint. So that's x squared plus y squared equals 9. And that's how I make sure I have enough equations to deal with all the variables that we have. Without writing this third equation, we'd have only 2 equations and 3 variables. But now we have 3 equations and 3 variables. Okay, so now we need to solve this system of equations. Okay, so let's begin with one of these equations. So I'll begin with 1. And remember, we've talked about don't divide both sides by 2x to cancel it out, because what if x was 0? If x was 0, we'd be dividing by 0 and possibly lose the solution. That would be bad. Instead, move everything over to one side. So 2x minus 2 lambda x equals 0. And then factor that thing out. So factor out the 2x. And then I'm left with 1 minus lambda equals 0. And now there's 2 possibilities. Well, what if, the first case is, what if this part equals 0, the 2x? And if that equals 0, if 2x equals 0, well then x equals 0. And if x equals 0 and you plug that into equation 3, you'll get y squared equals 9. And then square rooting both sides, we would get that y equals plus or minus 3. Okay, so we have some possible points to check. When x is 0, we're getting that y is 3, and y is also negative 3. Okay, so what if now the second term here is 0? So if 1 minus lambda equals 0, then what do we get? Well, then we get that lambda equals 1. Okay, so let's take that value, lambda equals 1, and let's substitute that into another equation. So let's take lambda equals 1, and let's substitute that in. Let's substitute that into equation 2, because equation 2 has a lambda in it. So that'll give me 2y minus 2 equals 1 times 2y. And with this, I could subtract both sides by 2y and get that negative 2 equals 0. But negative 2 doesn't equal 0. That's not true, which means we get no solution in this case. So no solution, I'll put a sad face, because that's a little disappointing. We were hoping to get a solution, possibly, and we didn't get one. So from the case when 1 minus lambda equals 0, we just didn't get a solution. Okay, but that's actually not terrible, because in terms of how much work we have to do, it's less to check now, and that's what our next step is going to be. It's going to be to check the points that we have so far. So we are ready to, check which solution that we have is an absolute max and which is an absolute min by plugging the points that we have. Let's write that better. Plugging the points, the solutions that we got, into the original function f. So before I do that, there's one thing that I want to go back and mention, which is with Lagrange, we've said before that the solutions that we get, they might correspond to local mins or local maxes. That's what Lagrange can help us find on an immediate sense. So how come in this problem we'll be able to find the absolute max and the absolute min by doing this? So the reason for that has to do with our constraint here. So our constraint x squared plus y squared equals 9, the graph of this is a circle centered at the origin of radius 3. So 3, 3. And this is a closed region because it consists of its boundary. It consists of just all the points on the circle. That's the boundary of this region. It's closed and it's bounded because it doesn't go off to infinity anywhere. It's a closed and bounded region. And we reviewed this in the previous video. But when we have a function and we're looking at it on a closed and bounded region, our function, in this case f, will attain its max and min, somewhere on this region. So when we use Lagrange and we set up this system of equations and we solve that system of equations, the solutions that we get, in this case they were 0, 3 and 0, negative 3, those are possible candidates for local mins and local maxes. But in this problem, because our constraint is a closed and bounded region, we know that f has to have its absolute max and min occur somewhere. So those absolute max and absolute min have to be at one of these candidates for the local max and the local min. Okay, so let's now find them. Let's plug these values in. So let's remember that our function f of x comma y was equal to x squared plus y squared minus 2y. So let's first plug in the point 0, 3. So x is 0, so we'll get 0 squared plus 3 squared, plugging in y, and then minus 2 times 3. So we'll get 9 minus 6, which is 3. And now plug in the other point, f of 0, negative 3. So x squared will get 0 squared plus y squared will get negative 3 squared, and then minus 2 times y, 2 times negative 3. Okay, so we have 9 plus 6, which is 15. Okay, so the largest of these is going to be our absolute max. So this is our absolute max value. This is our absolute max value. And the smaller of these, the smallest of these is going to be the absolute min value. So that's 3, the absolute min value. And that is our answer. So the two key things that I want you to be able to take away from this example is, 1, understanding this method of Lagrange multipliers, how to find the function f, how to find the function g, how to set up our system of equations, and then maybe the hardest part of that is how to solve the system of equations. So the first part again that I want you to take away is being comfortable with the process of Lagrange multipliers. The second part that I want you to take away from this, and this is the more conceptual part, is Lagrange usually is a process that we use to determine local mins and maxes of a function that's subject to a constraint. So I want you to understand how come in this problem we knew for sure that there was going to be an absolute max and an absolute min. And then what we did to find the absolute max and the absolute min at the end by plugging in points. All right, so in terms of our goals for this section, we have finished our last goal over the course of these few videos. We've done just more examples getting comfortable with the method of Lagrange multipliers. And what I want to leave you with is, this was our last new section in Math 13. In our class, this is our last new section to cover. So take a minute and celebrate. This is an awesome achievement. We've made it essentially to the end of all of the new content in our class. So take a minute, celebrate. So if you've made it this far, really awesome work to persevere and really push through all of this content. We've navigated a lot of new stuff, a lot of challenging material, and I appreciate all the awesome work that you've put in so far. So the plan for our last 2 lectures will be to do review videos for our final exam.